we're going to start talking about some different types of reactions. We're talking about precipitation reactions, oxidation reduction reactions or redox reactions, and acid-base reactions. First, let's talk about precipitation reactions. An insoluble product that separates from a solution is called a precipitate. You've heard the word precipitation most of your life when you hear about the weather outside, something falling from the sky. We're talking about solids that fall out of solution in a beaker, for example, when we mix a couple of chemicals together. And so let's take something like sodium iodide, it's ionic, it's aqueous, and lead nitrate, it's ionic, it's aqueous. When we write those as being AQ, that means in solution they have dissolved and they're dissociated. So we've got sodium ion plus iodide ion, and we got lead ion and nitrate ion. And so in solution, we've got two beakers there now shown. One of them, we got sodium ions and iodide ions. They're free to move about. They're dissolved and dissociated. It's a colorless solution. You can see that by looking at the beaker. In the other beaker, we've got some lead nitrate. The gray balls of Pb2+, the gray spheres, and then the little red spheres are the oxygens with the blue sphere that's a nitrogen. And they're dissolved and dissociated. They're free to move about. We got two homogeneous solutions. Now let's pour them together and watch what happens. And so as we pour them together, this yellow cloud forms. And what we see being formed is lead iodide, a yellow precipitate. So the sodium iodide plus the lead nitrate is reacted, and the lead 2+ ion is now reacted with the I- iodide ion from the sodium iodide to make lead iodide, actually lead 2 iodide, if we use the correct stock nomenclature. So that's a solid, that's the yellow substance that you see. And then we've made some sodium nitrate that's still dissolved and dissociated. It's still in the solution. So we've got this yellow precipitate, a yellow cloud that's being formed. And if we let it sit for a little while, the lead iodide will settle out of solution. It precipitates, it falls out. Gravity will take it down to the bottom. And so at the bottom, that yellow layer is lead iodide. The sodium ions and nitrate ions are still dissolved and dissociated, and they're free to move about in the solution. Now, if we were to be able to decant that liquid, which means to pour it off, and we have this solution of just sodium nitrate ions, we evaporate all the water, we would then have left sodium nitrate solid. So what we're going to need to be able to do is we're going to need to be able to predict when we mix two solutions together whether a reaction will take place, whether or not a precipitate will form. So solubility is defined as the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. Solubility is the maximum amount of solute, the substance that present in lesser amount in a solution, that will dissolve in a given amount of solvent at a specific temperature. You change the temperature, you change the amount of solute that can be dissolved. Typically, when you increase the temperature, you dissolve more solute in a solvent. When you make sweet iced tea, for example, what do? You boil the water to steep your tea, yes, but also before you do that, or as you do that, you go ahead and dissolve your sugar in there because it is more soluble at that higher temperature. So you only dissolve so much of a solid in any amount of solution. Yes, salt will dissolve in water, but if you take a whole pound of salt and put it in a small glass of water, all of it's not going to dissolve, of course. But there are some compounds that are insoluble. That means they don't become solubilized in water. And I'm talking about some ionic compounds in particular as these reactions that we're going to talk about. So we need to learn some guidelines for what's soluble, what's not soluble. So let's first go through the water-soluble compounds, those things that will dissolve and dissociate in water that are soluble. And we'll list those, and we'll talk about some of the exceptions that they have. First classification of compounds that are always soluble, no matter what. And we're looking at ionic compound, a metal plus a non-metal, or a polyatomic ion that's in there. So compounds that contain an alkali metal, those are our group 1As. So sodium, lithium, sodium, potassium, rubidium, cesium, or the ammonium ion. If that's in a compound, it's going to be soluble. Those ions are always soluble. And the compounds that are associated, the anion that would be associated with them is also soluble. Compounds contain the nitrate ion, NO3-, the acetate ion, C2H3O2-, or the chloride ion, ClO3-. If a compound contains one of those anions, it's going to always be soluble in water. If a compound contains the chloride ion, or the bromide ion, or the iodide ion, Cl-, Br-, or I-, they're soluble in water, except if the cation that they're associated with is the silver ion, Ag+, the mercury 1 ion, Ag2, 2+, or the lead 2+ ion. If those anions are with those cations, that compound will be insoluble. It'll precipitate. So, example of that be silver chloride, or mercury iodide, or lead bromide. If you have those compounds, they will be insoluble. So, compounds contain the sulfate ion are always soluble, except if that sulfate is with silver, Hg2, 2+, lead 2+, calcium 2+, strontium 2+, or barium 2+. So the silver ion, the mercury 1 ion, lead ion, or those 2A alkali earth anions, cations, excuse me. So those are the compounds that are always soluble with a few exceptions. Now we're going to look at the compounds that are always insoluble, except for their exceptions. So the following polyatomic ions, if you find them in solution, that compound will be insoluble. So compounds contain the carbonate ion, CO3-2-, the phosphate ion, PO4-3-, the chromate ion, CrO4-2-, or the sulfide ion, S2-. They're always insoluble, except if those polyatomic ions are with these cations: lithium, sodium, potassium, rubidium, cesium, or ammonium. Remember, back to the previous slide, with those compounds, if it contained those ions, they were always soluble. Well, here's an example where those cations are with anions that otherwise would be insoluble. It makes them become soluble. Compounds containing the hydroxide ion are insoluble, unless, once again, you've got one of these cations that always makes it soluble: lithium, sodium, potassium, rubidium, cesium, or barium. So carbonates, phosphates, chromates, sulfides, and hydroxides, they're insoluble unless they're with one of those 1A ion cations or ammonium. So we're going to be talking about 3 different types of equations that we want to utilize as we talk about precipitation reactions. There's going to be a molecular equation that we can write that's sort of the overall reaction, where it's going to contain all the species that are involved as if they were molecules. More about each of these in just a moment. I'm just listing them to begin with. There's going to be an ionic equation that shows everything that's in the reaction, but it's also going to show those compounds that dissociate into ions as those individual ions. Sometimes some books will refer to that as the total ionic equation. And there's the net ionic equation. It's only going to show those species that change from the reactant side to the product side. Let's talk about all these 3 in more detail and give you an example of each. pH. So in the molecular compound, those compounds are represented by chemical formulas as though they exist in solution as molecules or formula units. Move me out of the way. So molecular equation, the compounds are represented by chemical formulas as though they exist in solution as molecules or formula units. For example, sodium sulfate plus barium hydroxide reacts to make sodium hydroxide and barium sulfate. So this is the molecular equation. We're leaving everything as compounds. So sodium sulfate, aqueous, that means it's going to be dissolved and dissociated in water. You would have sodium ions floating around free and sulfate ions floating around free. Barium and hydroxide, that's aqueous. Remember, hydroxides are insoluble except with barium. And the previous, and also the sulfates and sodium ions, they're always soluble, except sulfate has some exceptions, and this is where we're going to see that. So we mix, if we had two beakers, we can mix them together. The sodium sulfate would be a clear aqueous solution. The barium hydroxide would be a clear aqueous solution. We pour them together, we see a white cloud. What that white cloud is going to be is barium sulfate. Remember, this exception for sulfates where make it insoluble is with a barium ion. So that's going to be solid. Sodium hydroxide, this is going to still be present in solution as dissociated ions because all sodium compounds are soluble in solution. And so we got this equation where everything's written together as a compound. And so that's what the molecular equation is. Now we're going to take the same reaction and write it as an ionic equation. And when we do that, the compounds that exist completely, predominantly as ions in solution, we're going to represent those as those ions. So let's see an example. So we just took the molecular equation, and now we're going to write from that the total ionic equation, or ionic equation. So sodium sulfate, we're going to write as the two sodium ions, aqueous, plus the sulfate ion, aqueous, plus the barium 2+ ion, aqueous, plus 2 hydroxide ions, aqueous. Those are our reactants. So everything that dissociates into ions, we write as those particular ions. That's on the reactant side. On the product side, those things that are soluble, that dissociate, we're going to keep those as ions. So we have 2 sodium ions plus 2 hydroxide ions. But when we pour those solutions together, the white cloud that we form with barium sulfate. It's insoluble. So we'll write that as barium sulfate, the solid. So everything that's aqueous means it's dissociated. The thing that doesn't dissociate, we're going to write as a solid. So that's our ionic equation. Next, what we're going to do is write the net ionic equation. The net ionic equation is only going to show those species that actually change from one side to the other. And so let's look at what's on the reactant side versus what's on the product side. So on the reactant side, we got 2Na plus. We got 2Na plus aqueous on the right-hand side, the product side. And so just like in algebra, if you got the same thing on both sides of the equation, you cancel them out. So the sodium ions are going to cancel out. We've got SO4 2- aqueous on the left-hand side, but now on the right-hand side, the product side, we don't see SO4 2- as aqueous. It's part of barium sulfate. So that's changing from one side to the other. The barium 2+, likewise, on the right-hand side is barium sulfate. And so it's changing from one side to the other. And the hydroxide ion, present, there are 2 of them on the left, the reactant side, 2 of them on the right, the product side. And so that's not changing. So as we write the net ionic equation, we're going to leave out those species, those ions that appear on the same side, appear on both sides of the reaction area. They're spectators. they don't participate in the reaction. And so sodium ion and hydroxide ion, those are the spectator ions in this reaction. So we cross those out and then write the net ionic equation. It only shows those species that are actually involved in the reaction, the net ionic equation. And so it's barium ion, barium 2 plus aqueous sulfate aqueous makes barium sulfate. That's a solid. And that's the net ionic equation. And so before we leave this chapter, you've got to be able to take a couple compounds that are soluble and figure out what they're going to make when you mix them together. If they do react to make a precipitate, you'll need to be able to write the molecular equation. You need to be able to write the ionic equation, and then you'll need to be able to write the net ionic equation.